All right, here we go. Desmos 14. Oh, it's the last Desmos. You'll get that one? You remember when that happened? All right, so in this Desmos, you're going back to the Squid games. And so as we can see here, we only have a rate out. And what we're going to do is notice that this differential equation K, which is the constant of proportionality, which is this negative 0.0072 value, we are going to actually write out the solution. So you can see the K will go right there, and then we'll figure out how we find these other values. So I know it needs to look something like this. So I know it can't be that one, right? And so it says the initial volume. So the initial is if you let T equals 0, then your initial would be 58. So I know it can't be this one because K is the negative 0.0072. And I know it can't be this one because that one, I'm sorry, this one because it's not negative. So it must be that one. Yes, that is correct. Thank you, cowboy emoji. And so now from here, actually, these are a lot easier to do than what you did in the last activity with the differential equation, because all you're doing is putting the value of T. And so, of course, we would expect for it to start at 58. And then when I put the 60 in, you'll see that these values will be a little off. Remember that the differential equation is an approximation and this is the actual solution. So you're going to do the same thing here where you're giving the half-life of warfarin is 39 hours, and to solve this differential equation, and I'll kind of skip ahead to show you that this is how you're going to set it up. So you're going to do this here, but I'm kind of helping you. And so I set up the half-life, the half of the quantity that is there equals the quantity e to the negative k 39. Where'd the 39 come from? I don't know. Right there, 39 hours. Okay, so when you go through and you solve this for k, you should get this value. All right, so now that I have this value, I want to be able to solve this differential equation, and it says for 30 being reduced to 35%. Let me see if I put anything here. No hints. Sorry, didn't help you there. So you're going to do the same exact thing here, except 0.5. You'll put 0.35 for 35%, and then you'll put your K value because you're actually solving for time. Do you know what I'm talking about? You're like, no, please help us. So it'll be the same exact thing. But then this will be that negative 0.01777, and then you're solving this for T. And if you're wondering, like, what happens to the Q's? They divide out, right? And so this will be the same technique. All right, if you could have any superpower to make students pay attention. I got jokes, yeah. All right. What if we have both a rate in and a rate out, which this should look familiar, then this is the solution. And now what you're going to see is when your first step when you have something like this, you factor out the K. The K, the constant of proportionality, a proportion is a decimal, so I know that this is going to be brought out front. What's going to be left on the inside will be dividing these values. So minus 0.1 divided by 0.1 and Q. And in this case, with it being an out, I want to do the negative of this value. And I think I show the solution, yeah, right here. But this is how I do this. Students always wonder, how do you get that 850 here? You're dividing out this negative 0.1. And so here, you can solve this. It says write the solution, or Q of 0 equals 0. So meaning that the initial amount, nothing is there. I will show you this solution here, but you should be able to go through and solve this for C on your own. Now, once again, here, you're just plugging in these values in here. All right, graph differential equations, explain what you think is happening here in the long run. Same thing with the metformin. We're trying to see what this value is going to, okay? And we typically, in a course, when we're looking at something like this, and I'll kind of mention it here when I get to that next slide, is when we're wanting to see what is happening in the long run. When we're looking at a drug, we don't really call this carrying capacity anymore. We call it equilibrium. And equilibrium is also where the differential equation equals 0. Remember that, because in the milestone, you're going to have to find the equilibrium. You just set your differential equation equal to 0. So, speaking of the milestone, we will talk about this in the group work, but this should look very familiar to you. We did this this first table in our last group, but now I've added the exact, so this is exactly from your lecture notes that we ran the code here, but you will get more of this again in the group work. And that is it. You're almost done. Hope you survive. Y'all got this. I'll see you this week.